In this module, we will study the equilibrium of concurrent force systems and use what we will call the Acer's method. So any system that is in static equilibrium has the property that the net sum of the forces on that system equals 0. And we can express this as the sum of the force equals 0. Notice that this is a vector equation. That's why everything is in bold. But it could be rewritten in terms of its components in x, y, and z, although for now we are only studying the x and y two-dimensional version. Remember, before any equations can be written, a clear free body diagram must be drawn to show exactly which forces are in the equation. I'll refer you back to the modules D2 for details for drawing the free body diagrams. And because of a change that was made this semester in how I'm organizing the discussion of free body diagrams, some topics have been moved to C1. So in this module, if you hear a reference to the concept of action-reaction or the exploded free body diagram, those will now be covered in module C1. However, it's totally fine to get a preview of those ideas here, so I decided not to just change the modules. I'm going to leave it in here. But just be aware that I'll cover that more in detail later, and for the purpose of this module, I think everything will be fine. Let us also come back to this fundamental principle of mechanics. The part 1 we discussed in the last module, you can draw a free body diagram of anything. Part 2 then says, if an entire system is in equilibrium, then so is any subsystem or part of that system. That means that the law of equilibrium applies equally to the entire system as it does to any subsystem. So when I say you can draw a free body diagram of anything, that also means that you can then apply the law of equilibrium to that thing that you drew. The Acer's method will be summarized through the following set of procedures. A, we will determine the appropriate subsystem or body to study. C, we will count the number of unknown reactions in our system. E, we will write the equilibrium equations. R, we will rearrange those equations into a standard form. And S, we will solve the equations and summarize the results. So for example, we've seen this picture before. Let us now suppose the cylinder D has a mass of 60 kilograms. And now our question is, determine the forces in the cables AB and BC. We saw before that we could draw an exploded system diagram in which we break up the system into many small subsystems or pieces, and we draw the free body diagram of each of those pieces. And now the question will be, yes, it is true, the law of equilibrium applies to each of these pieces, but which piece or pieces are the ones that will be useful to solving our problem? Before proceeding, we should also explain what we mean by a concurrent force system. In a concurrent force system, all forces pass through a common point, and there are no torques on that system. And remember that each of these diagrams here, even though it came from one total system initially, now that we've divided it into parts, each of those parts is considered a subsystem, and they can also be considered to be concurrent force systems. So for example, if we look at the system of the cylinder and that segment of cable, that's a concurrent force system, and you can see by the blue dot, both the weight and the FBD force pass through that point. If we look at the system of the ring B, all three of those forces in that system pass through the point B, FAB, FBC, and FBD. They all intersect at point B. And likewise, if we look at those cable segments, either the segment of AB or the segment of BC, In each of those cases also, the forces pass through a common point somewhere in the middle of that cable section. We will also note later on, we will study force systems that are not concurrent force systems, and in those cases we will also have to study the sum of moments, but for now in this module we'll focus on concurrent force systems, and therefore we have only the sum of the forces to accomplish at this point.
So it might seem obvious or natural to say, well, look, the question asks us to determine the force in each cable. So let us in fact use the drawing of each segment of the cable, and that might be the way to solve the problem. So let's try that. And to get started, let me invent the direction U, which is parallel to the AB cable. If we consider the sum of the forces applied to that cable AB, then this is the same as summing the forces in the U direction. So if I write that equation, the sum of the forces in the U direction, I have one force is plus FAB, and the other force is negative FAB, and therefore they automatically sum to 0, which is true, but an equation that says 0 equals 0 is not usable to solve what we were asked to solve. Notice also that these diagrams by themselves did not have any of the given information, meaning that the 60 kilogram mass is nowhere in these diagrams, which is also another clue that these diagrams by themselves are not useful. I want to make another note before we go on. Some people say in these diagrams that the forces in each diagram are equal because of the law of action and reaction, but in fact, look carefully, the colors of the tilde are different. The action-reaction principle applies when we gave the same color, meaning the same cut surface, and you have the twin forces acting on each other, whereas here, if I have some length of a cable, the force FAB at the yellow point, for example, is not at the same point as the FAB at the green point. And so the law of equilibrium tells us that these forces must be equal, but these are not action-reaction pairs. Okay, so having discovered that looking at the cable segment itself is not going to help us, let us consider these other two parts of the system. One is a diagram of the ring B, and the other is a diagram of the cylinder D. And here we might suspect that there's a better chance of solving the problem, at least because in the cylinder of D, the weight is given, and that might help us to solve the problem. And notice here I've now calculated the weight from 60 kilograms, multiplying by 9.81 meters per second squared, and giving us 588.6 newtons. Okay. So before we go on any further, let's count. Let's count the number of unknowns in these diagrams. And I count FAB, FBC, and FBD. There are 3 unknown variables in these 2 diagrams. And notice I'm counting FBD once, not twice. Why did we do that? Because our next step to write the equations, in general from mathematical reasoning, we should expect to have the same number of equations as we have unknowns, and so that's why we want to count the unknowns ahead of time so we have some idea that our equations are also in the right direction. Now in this case, let's say the cylinder D looks more simple to work with, and that's because everything is in the same direction, and we can guess that might be a simpler equation to write. So if I apply the principle, the sum of the force equals 0 to the cylinder of D, the only forces are in the J direction. So I have FBD times J minus W times J equals the 0 vector, which could be then written as 0I plus 0J. And if I then go on to solve this, I'll divide that system into an I and J component. And so in the I direction, we have a 0 equals 0. But in the J direction, we have FBD minus W equals 0. And if we solve that very simply, we get FBD equals W equals 588.6 newtons. And I'll note that this result for BD applies therefore to both of the places in this set of diagrams where the BD force occurs. Let me also say that maybe you thought it was obvious that FBD should equal the weight, and I think in statics that is obvious, but if you were doing dynamics where there might be accelerations, I'll advise you to think ahead that this might not be true. Okay, so in statics it might seem obvious, but I'm trying to assume it's not obvious and go through the full calculation step. Okay, so having said that, if we come back to our diagram for B, I'm now going to replace the weight with now the known value of 588.6 newtons. Okay, and now we have two unknown forces remaining on this diagram. And again, in vector form, I can write the vector of AB plus the vector of BC plus the vector of BD equals 0. And if we think about writing this in that format that we learned in the last modules about any vector being a product of a scalar and a direction, I'll now understand that the FBA vector is the FBA scalar times the unit vector in the BA direction, and then FBC vector is FBC scalar times unit vector BC, and FBD vector is FBD scalar times unit vector of BD, and that all sums up again to equal 0. So let's draw those unit vectors. This one is easy. The unit vector of BD is negative j. The unit vector for BC is the square root of 2 over 2i plus the square root of 2 over 2j. And the unit vector in the BA direction is negative 4/5 I plus 3/5 j. And if you want to review how we got those, go back to the modules D2. Okay, so given that this is our now equilibrium equation, but we know unit vectors, I'm going to substitute each unit vector for the expression we had in the previous slide. And so therefore I have FBA times negative 4/5 I plus 3/5 j plus FBC times square root of 2i, square root of 2 over 2i plus square root of 2 over 2j, and then plus 588.6 newtons times the negative j vector, that all equals 0, 0 vector. Now, what we're going to do is, as we've seen before, is we can divide this equation into the I and j components. And here's where I want to introduce this standard form, where notice I've put all of the same variables in each equation in the same column, meaning they're lined up. And on the right-hand side, I'm going to move anything that has a known value over there. So on the left, we have unknown terms. On the right, we have known terms. And if I do this with the actual numbers,
I do recommend that you take a slight pause before passing to the next slide, and you try to fill in these equation parentheses yourself. And after you've done it, then you can proceed to the next slide and compare your answer with what I'm recommending.
I'll now put in terms of decimals, negative 4/5 is negative 0.8, and that multiplies FBA. And then the square root of 2 over 2 is approximately 0.7071. That multiplies FBC, and that equals 0 in the I direction. And in the J direction, I've got 3/5 or 0.6 FBA plus 0.7071 FBC. And now, because I had initially negative 588.6 newtons J, I put that on the other side, and now it becomes plus 588.6 newtons. Okay, so think about that for a second. This R rearrangement step is important. I want this to be clear in your mind. Okay, now I'm not going to go through solving this. I believe you understand how to solve systems of equations, but this is a system of two equations and two variables. And again, that counting principle is important. That balance of equations and unknowns should generally occur. If I solve these equations, you can check me. I determine FBA is 420.43 newtons, and FBC is 475.66 newtons. So if I summarize the results, one way I can do that is by drawing the force polygon associated with the sum of the forces equaling 0. And going back to what we did with resultants earlier, we said the force polygon is a path. Well, now if that path adds up to 0, it means we start and finish at the same point. So let's draw, first of all, the vertical vector that was given, 588.6 newtons. And let me say I'll next add to it the FBC vector, which again goes at a 45-degree angle northeast. And then to get back to the beginning of the green arrow, I connect the other vector, which is now the force of BA. And if I did this properly to scale, the lengths of all of those vectors should be the same as the values we calculated. And that, of course, assumes that I drew the angles approximately correctly. And maybe my diagram here isn't quite exactly right, but it's approximately correct. So I want to encourage you to do this last step as a way of summarizing the result and making sure everything makes sense. And finally, it's a good exercise to put into words what you see. So for example, an engineer might say, now I can really see that the reactions in the cables are less than the applied load, and that kind of makes sense because we would like to have a system maybe that can carry a big load where each cable by itself has a smaller load. On the other hand, this might not always be the case. If you were to change the cable angles, this would have a significant effect on the cable force, and some other problems that we might see later will explore that. So that concludes this module.